There's something we got wrong about dinosaurs. Not about their extinction, not about their size, but about their rise. For 150 years, we've told a story of inevitable triumph. Dinosaurs appeared in the Triassic period, around 230 million years ago, and immediately began their march toward global dominance. Superior design, better physiology, evolutionary destiny. Within a few million years, they ruled the planet, or so the story goes. Except that's not what happened, not even close. For the first 30 million years of their existence, dinosaurs were nobodies. Marginal predators the size of chickens and turkeys, skulking in the shadows of the real rulers of the Triassic world. Those rulers weren't dinosaurs. They were crurotarsans, land crocodiles, and they were bigger, faster, more successful, more diverse. For 3 decades of the Triassic, these creatures dominated every terrestrial ecosystem on Earth, while dinosaurs remained rare, small, and utterly insignificant. Then, 201 million years ago, something catastrophic happened. A mass extinction, the second worst in Earth's history. And when the dust settled, the crurotarsans were gone, extinct, every last one. And the dinosaurs, those marginal failures, inherited an empty planet. So here's the question we should be asking. Why did the winners lose? Why did the most successful reptiles of the Triassic vanish completely, while the losers went on to dominate the Mesozoic for the next 165 million years? Was it superiority, or was it just dumb luck? Welcome to Triassic Earth, the world between apocalypses, where the birth of the dinosaurs was anything but inevitable. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. To understand why dinosaurs were such failures in the Triassic, we need to understand what the Triassic actually was. And to understand that, we need to go back slightly further, to the single worst day in the history of complex life on Earth. 252 million years ago, the end of the Permian period. Life on Earth had been evolving for over 3 billion years. Bacteria, algae. Then, 600 million years ago, animals. The Cambrian explosion. Gradually, over hundreds of millions of years, life colonized the land. Plants, insects, amphibians, then reptiles. By the late Permian, Earth's continents had collided into a single supercontinent called Pangaea. And that supercontinent was covered in forests, swamps, deserts, mountains, an entire world teeming with bizarre creatures that look nothing like anything alive today. Therapsids, mammal-like reptiles, some the size of hippos, herbivores with tusks and beaks, carnivores with saber teeth. These weren't dinosaurs. Dinosaurs didn't exist yet. They wouldn't for another 20 million years. The Permian was the age of the therapsids. They were the dominant land vertebrates, the apex predators, the megaherbivores. If they'd survived, if the Permian had continued peacefully into the Triassic, mammals might have evolved tens of millions of years earlier, and dinosaurs might never have gotten their chance. But the Permian didn't end peacefully. In what is now Siberia, something went catastrophically wrong with the planet's geology. Magma, rising from deep within the mantle, found a weakness in the crust, and it erupted. Not a single volcano, an entire volcanic province, millions of square kilometers. Lava flows hundreds of meters thick, spreading across the landscape like a slow-motion flood, releasing gases, carbon dioxide, sulfur dioxide, methane from burning coal seams beneath the surface. And this wasn't a brief eruption. It lasted 1,000,000 years. Some estimates suggest longer. 1,000,000 years of continuous volcanic activity, pumping greenhouse gases into the atmosphere at a rate that makes modern human emissions look trivial. The climate spiraled out of control. Global temperatures rose by 10 degrees Celsius, maybe more in some regions. The oceans warmed, stratified, stopped circulating. Oxygen levels in the water plummeted. Hydrogen sulfide, normally locked in deep anoxic sediments, began bubbling to the surface, poisoning the atmosphere. Acid rain fell. The ozone layer thinned or collapsed entirely, bathing the surface in ultraviolet radiation. On land, forests died, rivers dried, deserts expanded. And life nearly ended. 96% of marine species went extinct. Trilobites, which had survived for 300 million years, gone. Tabulate and rugose corals, gone. Most brachiopods, most crinoids, most bryozoans, gone. The ocean ecosystems collapsed so completely that it took 10 million years for coral reefs to return. On land, 70% of vertebrate species disappeared. The great Therapsid dynasties wiped out. The mega herbivores extinct. The apex predators gone. Forests reduced to fern prairies and moss-covered wastelands. Insects, which normally dominate terrestrial ecosystems, suffered their only known mass extinction. This was the Permian Triassic extinction event, the Great Dying, and it nearly ended complex life on Earth. When the volcanic eruptions finally subsided, when the carbon cycle began to stabilize, when the first rains of the Triassic began to fall, the planet that emerged from the catastrophe was almost unrecognizable. Pangaea still existed, but now it was a wasteland. A hot, dry, oxygen-poor wasteland where survival was a daily struggle. This is the world into which the dinosaurs would eventually be born. But not yet. Not for another 20 million years. First, life had to figure out how to survive. The early Triassic, the first epoch after the extinction, was a world in recovery. But recovery is the wrong word. It implies a return to what was before. That's not what happened. The early Triassic was a fundamentally different planet. Hotter, drier, more hostile, and the life that survived wasn't the same life that had thrived in the Permian. In the immediate aftermath of the extinction, fossil diversity collapsed. In the Permian, if you walked through a forest or along a riverbank, you'd encounter dozens of different species of therapsids, reptiles, amphibians. In the early Triassic, you'd encounter one, maybe two if you were lucky. That dominant species was Lystrosaurus, a therapsid, a survivor, about the size of a pig, with a barrel-shaped body, short legs, and a beak for cropping vegetation. Lystrosaurus wasn't impressive. It wasn't fast. It wasn't smart. It wasn't particularly well adapted to any specific environment. But it survived. And in the devastated ecosystems of the early Triassic, survival was everything. Fossil beds from the early Triassic show Lystrosaurus making up 90 to 95% of terrestrial vertebrate fossils. Not because it was successful in the Darwinian sense, competing and winning against other species, but because there were no other species. It inherited an empty planet, and it spread across Pangaea, from what is now Antarctica, to Russia, to South Africa, to China. Everywhere paleontologists look in early Triassic rocks, they find Lystrosaurus. This is called a disaster taxon, a species that thrives not because it's superior, but because everything else is dead. And it wasn't just on land. In the oceans, a similar pattern emerged. Before the extinction, marine ecosystems were dominated by complex food webs, predators, herbivores, filter feeders, scavengers, dozens of ecological niches, all filled. After the extinction, those niches were empty, and the few species that survived, opportunistic generalists, spread into every available space. One genus of bivalve mollusk, Claria, makes up over 90% of early Triassic marine fossils in some locations. Again, a disaster taxon, thriving in the absence of competition. This is what the early Triassic looked like. A world of weeds, generalists, survivors clinging to existence on a hostile planet. And this state of affairs lasted for millions of years. 5 million, 10 million. Longer than the entire history of the genus Homo. Longer than the age of grasslands. An incomprehensibly long span of time where Earth remained locked in a low-diversity, high-stress ecological state. Why did recovery take so long? Several reasons. First, the environmental conditions remained harsh. Temperatures stayed elevated. Oxygen levels remained low, around 12% compared to 21% today. That's enough to sustain life, but not enough to sustain high activity levels or large body sizes. Organisms were metabolically limited. Second, the extinction had been so severe that entire ecological structures had collapsed. Predator-prey relationships, symbioses, food webs. These things don't rebuild quickly. They require diversity. And diversity requires time and evolutionary experimentation. In the early Triassic, there simply weren't enough species to form complex ecosystems. And third, the planet kept getting hit. The Permian-Triassic extinction wasn't a single event. It was a cascade of crises. The Siberian Traps eruptions continued intermittently for millions of years. Climate remained unstable. Ocean chemistry fluctuated. There's evidence of multiple smaller extinction pulses throughout the early Triassic, each one knocking ecosystems back before they could fully recover. It was into this world, this hot, unstable, ecologically devastated world, that the archosaurs emerged. Archosaurs, the group that would eventually give rise to dinosaurs, pterosaurs, and crocodiles. But in the early Triassic, they were small, rare, and not particularly impressive. Lizard-like reptiles, most no longer than a meter, scurrying through the fern prairies, hunting insects and small vertebrates, trying to avoid the few remaining large predators. And those large predators? They weren't archosaurs. They were therapsids, survivors of the Permian extinction. Cynodonts and therocephalians, dog-sized and wolf-sized carnivores, still clinging to their dominance. For the first few million years of the Triassic, the therapsids remained on top. Barely. Reduced in diversity and size, but still the apex predators. But slowly, over the course of the early and middle Triassic, that began to change. The archosaurs started to diversify, to grow, to experiment with new body plans. And by the middle Triassic, around 240 million years ago, the archosaurs had split into two major lineages. Two branches of the family tree, both successful, both diversifying rapidly, both competing for dominance in the recovering ecosystems of Pangaea. One branch would eventually produce the dinosaurs. The other would produce the Crurotarsans. And for the next 40 million years, it was the Crurotarsans, not the dinosaurs, that ruled the Earth. The Crurotarsans. If you've never heard the term, don't worry. Most people haven't. They're not as famous as dinosaurs, not as charismatic, not as heavily merchandised, but in the Triassic, they were everywhere. And they were spectacular. Crurotarsans are members of the Archosaur lineage that led to modern crocodiles. But calling them crocodiles is deeply misleading, because Triassic Crurotarsans didn't look like crocodiles. Most of them weren't aquatic. They didn't lurk in rivers waiting to ambush prey. They were terrestrial, active, diverse, and, in many cases, bipedal. Yes, bipedal. Two-legged land crocodiles running upright across the Triassic plains. Let me introduce you to a few. Postosuchus, a 4-meter-long predator from the late Triassic of North America. Postosuchus walked on all fours most of the time, but could rear up onto its hind legs when running or attacking. It had a deep skull, powerful jaws lined with serrated teeth, and claws on its forelimbs for grasping prey. Fossil evidence suggests it was an apex predator, hunting large herbivores and possibly other carnivores. And it was fast. Biomechanical studies of its limb proportions and joint articulations suggest it could run at speeds comparable to modern big cats. Saurosuchus, from Argentina, even larger, 7 meters long, over a ton in weight. A super predator with a skull nearly a meter long and jaws that could crush bone. Saurosuchus dominated the ecosystems of South America during the late Triassic. It was the lion, the tiger, the Tyrannosaurus rex of its time. Except it wasn't a dinosaur. It was a Crurotarsan, Fasolasuchus, another South American giant, possibly the largest land predator of the entire Triassic. Estimates suggest it reached 8 to 9 meters in length, comparable in size to the largest theropod dinosaurs of the Jurassic and Cretaceous. This thing was hunting dinosaurs, not the other way around. And it wasn't just the predators. Crurotarsans filled nearly every large terrestrial niche. There were herbivorous Crurotarsans called aetosaurs, armored like armadillos, some reaching 4 meters in length, grazing on vegetation like prehistoric tanks. There were omnivorous Crurotarsans, insectivorous Crurotarsans, even some that may have been semi-aquatic, though most were fully terrestrial. The diversity was staggering, and the fossil record makes it clear. From about 235 million years ago to 201 million years ago, Crurotarsans were the dominant large animals on Pangaea. In fossil assemblages from this time, Crurotarsans outnumbered dinosaurs by enormous margins. In some formations, 70 to 80% of large predator fossils are Crurotarsans. Dinosaurs are rare, sometimes absent entirely. So what about the dinosaurs? Where were they? They were there, but they were bit players, background characters in someone else's story. The first true dinosaurs appeared around 230 million years ago in the Middle Triassic, in what is now Argentina. Eoraptor, Herrerasaurus, small bipedal carnivores, no more than a meter or two in length, lightly built, fast, probably, but not powerful, not dominant. For perspective, imagine a modern ecosystem. Now imagine that the apex predators aren't lions or tigers, but house cats, and the large herbivores aren't elephants or rhinos, but rabbits. That's approximately the size disparity we're talking about. Early dinosaurs were small, and in a world of giant Crurotarsans, small meant vulnerable. The fossil record from the late Triassic confirms this. Dinosaur fossils from this time are rare and fragmentary. They're found in limited geographic areas. And even in those areas, they're vastly outnumbered by Crurotarsans, therapsids and rhynchosaurs, a group of herbivorous reptiles that were astonishingly common. Rhynchosaurs, another group you've probably never heard of. In some late Triassic fossil sites, Rhynchosaur fossils make up 85% of all vertebrate remains. 85%. These were pig-sized, beaked herbivores with specialized teeth for grinding tough vegetation. They were everywhere, filling the ecological role that would later be taken by herbivorous dinosaurs. But in the Triassic, herbivorous dinosaurs barely existed. There were a few early sauropodomorphs, the lineage that would eventually produce the giant, long-necked dinosaurs of the Jurassic. But in the Triassic, they were small, rare, ecologically insignificant. So why? If dinosaurs had all these supposed advantages, erect posture, efficient locomotion, advanced respiratory systems, why were they losing so badly to the Crurotarsans? The answer is simple. They didn't have those advantages. Or rather, the Crurotarsans had them too. Let's talk about posture. For decades, paleontologists assumed that dinosaurs succeeded because they evolved an erect, upright stance, with their legs directly beneath their bodies, rather than sprawled out to the sides like lizards and crocodiles. This upright posture, the theory went, allowed for more efficient locomotion, greater endurance, and the ability to grow larger. And that's true. Erect posture is advantageous. But here's the problem. Crurotarsans had erect posture too. Their legs were directly beneath their bodies, just like dinosaurs. They walked upright, they ran upright. Biomechanical analyses of Crurotarsan skeletons show that their locomotion was just as efficient as that of early dinosaurs. Maybe more so. Okay, what about metabolism? Surely dinosaurs had an advantage there. They were warm-blooded, right? Endothermic, high metabolic rates, capable of sustained activity, while Crurotarsans were cold-blooded reptiles, sluggish and dependent on external heat sources. Except that's not true either. Recent studies of Crurotarsan bone histology, the microscopic structure of their bones, show evidence of rapid growth rates and high metabolic activity. The same evidence we use to infer endothermy in dinosaurs. Some Crurotarsans, particularly the large predators like Postosuchus and Saurosuchus, were almost certainly warm-blooded, or at least had metabolic rates far higher than modern crocodiles. What about size? Dinosaurs got big, really big. Surely that was an advantage. Not in the Triassic. In the Triassic, Crurotarsans were bigger. Faseolosuchus was larger than any Triassic dinosaur. Saurosuchus was larger than any Triassic theropod. Even the herbivorous ictosaurs reached sizes comparable to or exceeding early sauropodomorphs. What about intelligence? Brain size? CT scans of Crurotarsan skulls, published in the last few years, show that their brains were reasonably well developed. Not as large relative to body size as those of theropod dinosaurs, but not primitive. Certainly capable of complex behavior, hunting strategies, social interactions. So, what's left? What advantage did dinosaurs have? As far as we can tell, in the Triassic, they didn't have one. They weren't better. They were just different. And in a world dominated by Crurotarsans, different meant losing for 30 million years. But then, 201 million years ago, something changed, something catastrophic. And it changed everything. The Triassic-Jurassic extinction, the fourth worst mass extinction in Earth's history, 76% of species gone, and among the casualties, nearly all the Crurotarsans, the great predators, the armored herbivores, the diverse, successful, dominant reptiles of the Triassic, extinct. And the dinosaurs? They survived. And when the dust settled, when the ecosystems began to recover, there were no Crurotarsans left to compete with them. The dinosaurs inherited the Earth, not because they won, but because their competitors died. So what killed the Crurotarsans? And why did the dinosaurs survive? That's the question. And to answer it, we need to understand what happened 201 million years ago. The end of the Triassic didn't arrive quietly. It arrived with fire, massive volcanic eruptions, even larger in some ways than the Siberian traps that had ended the Permian. This time, the eruptions occurred in what would become the Central Atlantic Magmatic Province, or CAMP. As Pangaea began to rift apart, as the Atlantic Ocean began to open, magma forced its way to the surface along thousands of kilometers of fractures. Lava flows covered enormous areas of what is now eastern North America, western Africa, and South America. The volume of magma erupted is estimated at over 2 million cubic kilometers, enough to bury the entire contiguous United States under a layer of lava 600 meters thick. And as with the Siberian traps, the problem wasn't just the lava. It was the gases: carbon dioxide, sulfur dioxide, methane from burning organic-rich sediments. These gases poured into the atmosphere for hundreds of thousands of years, maybe a million years, triggering rapid climate change. Global temperatures spiked. Estimates vary, but likely an increase of 3 to 4 degrees Celsius globally, with higher increases at the poles. The oceans warmed and acidified as they absorbed excess CO2. Marine ecosystems collapsed. Coral reefs vanished. Calcifying organisms, anything that built a shell or skeleton from calcium carbonate, struggled as ocean chemistry shifted. On land, the combination of heat, drought, and possibly acid rain devastated plant communities. And once again, life was pushed to the brink. Not as severely as the Permian-Triassic extinction, but close. 76% of species extinct, 20% of marine families, half of all terrestrial tetrapod genera. And among those losses, the Crurotarsans, almost all of them. A few aquatic lineages survived, the ancestors of modern crocodiles and alligators. But the terrestrial forms, the bipedal predators, the armored herbivores, the diverse and successful land Crurotarsans, gone, extinct. 40 million years of evolutionary success, erased in less than a million years. But the dinosaurs survived, most of them. Theropods, the carnivorous lineage, made it through relatively unscathed. Sauropodomorphs, the herbivorous long-necked lineage, survived and diversified explosively in the early Jurassic. Ornithischians, the other major herbivorous lineage, survived in smaller numbers but would later thrive. Why? What made the dinosaurs different? What allowed them to survive when the Crurotarsans didn't? Honestly, we don't know for sure. And that's frustrating, because this is one of the most important questions in the history of life. The answer determines why the Mesozoic belonged to dinosaurs instead of Crurotarsans. Why the largest land animals ever, the sauropods, were dinosaurs and not something else. Why birds exist today and not some descendant of Postosuchus. But we have hypotheses, several of them. Hypothesis 1. Respiratory efficiency. Dinosaurs, particularly theropods and sauropods, had a unique respiratory system involving air sacs. These are balloon-like structures connected to the lungs that allow air to flow in one direction, continuously, rather than in and out like mammalian lungs. This unidirectional airflow is more efficient at extracting oxygen. Birds, The living descendants of theropod dinosaurs have this system. It's one reason they can fly at high altitudes where oxygen is scarce. In the low oxygen environment of the Triassic-Jurassic extinction, when volcanic gases were filling the atmosphere and oxygen levels were dropping, perhaps this respiratory advantage made the difference. Perhaps dinosaurs could survive in conditions where crurotarsans suffocated. It's a compelling hypothesis. But there's a problem. We don't know for certain that Triassic dinosaurs had air sacs. The evidence for air sacs comes from skeletal features, hollowed-out vertebrae and bones that appear in some later dinosaurs. But not all early dinosaurs show these features, and we can't examine soft tissue in fossils. So it's possible, but not proven. Hypothesis 2. Dietary flexibility. Early dinosaurs may have been more omnivorous or generalist in their diets compared to crurotarsans. There's some evidence that certain early dinosaurs had broad diets, consuming plants, insects, small animals, whatever was available. Crurotarsans, particularly the large predators, may have been more specialized, obligate carnivores. And specialists, as we saw with the Ediacaran extinctions, are vulnerable during environmental crises. When prey populations collapse, specialists starve, generalists adapt. But again, evidence is limited. We can't know for certain what these animals ate. Gut contents are almost never preserved. Teeth can give clues, but they're not definitive. Hypothesis 3. Body size. Most Triassic dinosaurs were small to medium-sized, rarely exceeding 3 meters in length. Crurotarsans, especially the apex predators, were often much larger, 5, 6, 7 meters or more. Large body size requires a lot of food, a lot of energy. During an environmental crisis, when food becomes scarce, large animals starve faster than small ones. Dinosaurs, being smaller on average, may have had lower energy requirements and been better able to survive on limited resources. This hypothesis has merit, but it doesn't explain everything, because small crurotarsans also went extinct, and some dinosaurs were fairly large. Hypothesis 4. And this is the most recent and perhaps most intriguing: pure luck, contingency. The dinosaurs didn't survive because they were better. They survived because they happened to be in the right place at the right time. Because their geographic distribution, their habitat preferences, their ecological niches happened to be slightly less affected by the specific environmental changes of the Triassic-Jurassic extinction. Maybe they lived at higher latitudes, where temperature increases were less severe. Maybe they preferred upland habitats, which were less affected by oceanic acidification. Maybe they just got lucky. And that's an uncomfortable idea, because it means the dominance of dinosaurs for the next 165 million years, the evolution of birds, the entire shape of the Mesozoic era and beyond, might have been an accident, a coin flip. If the volcanic eruptions had been slightly different, if the climate had changed in a slightly different way, crurotarsans might have survived, and dinosaurs might have gone extinct. We like to think that evolution rewards the best. That success in nature comes from being stronger, faster, smarter, better adapted. And that's true, sometimes. But it's not the whole story, because evolution also rewards luck, being in the right place, having the right traits for circumstances you couldn't have predicted, surviving disasters that kill your competitors. The dinosaurs didn't win the Triassic through superiority, they won through survival. And that's a very different thing, but survival was only the beginning. Because after the extinction, after the crurotarsans were gone, The dinosaurs had to prove they could do more than just survive. They had to diversify, adapt, fill the empty ecological niches left by the extinction. And that's exactly what they did. Within 10 million years of the Triassic-Jurassic boundary, by the early Jurassic, dinosaurs had exploded in diversity. Theropods grew larger, developing into apex predators far exceeding their Triassic ancestors. Dilophosaurus, a 6-meter-long predator from the early Jurassic of North America. Cryolophosaurus from Antarctica, yes, Antarctica, which was much warmer then, another large theropod. And the sauropodomorphs. In the Triassic, they'd been small, rarely exceeding a few meters in length. But in the Jurassic, they became giants. Barapasaurus from India, one of the earliest true sauropods, reached lengths of 18 meters. Cetiosaurus from England, 20 meters. And these were just the beginning. By the late Jurassic, sauropods would reach sizes never seen before or since on land. Brachiosaurus, Diplodocus, Supersaurus, animals weighing 50, 60, 80 tons or more. The largest land animals in Earth's history. All descendants of those small, insignificant Triassic herbivores that had been pushed to the margins by rhynchosaurs and etosaurs. Why did sauropods get so large in the Jurassic? That's another fascinating question. Part of the answer is ecological opportunity. With the Crurotarsans gone, with the rhynchosaurs extinct, there was no competition for large herbivore niches. Sauropods could grow without being outcompeted. And their unique body plan, long necks, column-like legs, that air sac respiratory system, allowed them to reach sizes that other animals couldn't. But there's something else, something specific about the Triassic-Jurassic transition that may have enabled gigantism. And it relates to plants. The Triassic flora was dominated by ferns, cycads, and conifers. Nutritious enough, but not particularly abundant. Forests were patchy. Plant productivity was limited by the hot, dry climate and relatively low CO2 levels, ironically low compared to the Jurassic, despite the extinction having been caused by CO2 spikes. But in the aftermath of the extinction, as the climate stabilized, as CO2 levels remained elevated but stopped fluctuating wildly, plant productivity exploded. Conifers diversified, cycads spread, and crucially, the first seeds of certain plant groups that would later become dominant appeared. More plants meant more food. More food meant herbivores could grow larger, and larger herbivores meant predators could grow larger too. The Jurassic saw the beginning of an arms race between predators and prey that would continue throughout the Mesozoic. And it all started because the dinosaurs survived an extinction and their competitors didn't. So dinosaurs got lucky. They survived, and they capitalized on that survival. But here's the twist. They weren't done surviving, because the Triassic-Jurassic extinction wasn't the last mass extinction of the Mesozoic. There would be others, smaller ones in the Jurassic and Cretaceous. And then the big one, the Cretaceous-Paleogene extinction, 66 million years ago. The asteroid, the one that finally killed the dinosaurs. Except it didn't kill all the dinosaurs. It killed the non-avian dinosaurs, the large ones, Tyrannosaurus, Triceratops. The sauropods and hadrosaurs and ankylosaurs. But one lineage survived, the birds, avian dinosaurs, descendants of small theropods that had evolved flight in the Jurassic. So dinosaurs survived 2 of the 5 worst mass extinctions in Earth's history, the Triassic-Jurassic and the Cretaceous-Paleogene. They were survivors, professional survivors. And that, more than size or strength or intelligence, is what defined them. But we're getting ahead of ourselves. This is supposed to be about the Triassic, about what Earth was like during the birth of the dinosaurs. And we've covered the extinctions, the survival, the competition, but we haven't really talked about the world itself. What it looked like, what it felt like, what it would be like to stand on Triassic Earth and look around. So let's go there. Let's go back. Imagine you're standing in what will one day be Arizona. But it's not Arizona. Not yet. It's 220 million years ago, late Triassic, and the world is unrecognizable. First, the heat. It hits you immediately. A dry, searing heat that makes breathing difficult. The air temperature is pushing 45 degrees Celsius, over 110 Fahrenheit. And this isn't unusual. This is normal. Because you're standing near the equator of Pangaea, and Pangaea's interior is a furnace. There are no oceans nearby to moderate the temperature. The nearest coastline is thousands of kilometers away. You're in the heart of the supercontinent, and continental interiors, especially on a landmass as massive as Pangaea, get hot. Extremely hot. Computer models of Triassic climate suggest that equatorial regions of Pangaea experienced summer temperatures that would be lethal to most modern animals. 50 degrees Celsius or higher. Hot enough that vertebrates, anything with a backbone and a metabolism, couldn't survive for more than a few hours without shade and water. And shade is hard to find because the forests are gone. Not completely, but mostly. You're standing on a broad floodplain cut by seasonal rivers that are currently dry. The ground is reddish-brown, oxidized sediment, baked hard by the sun. Scattered across the landscape are clumps of vegetation, low ferns, cycads with thick, waxy leaves, conifers, but not the towering pines and firs you'd recognize. These are shorter, stockier, adapted to conserve water. Their needles are small and tough. Their bark is thick. In the distance, maybe a kilometer away, you see a larger stand of trees. A gallery forest following the course of a river that still has water, fed by distant mountains you can barely see through the heat haze. But between you and that forest is open ground, exposed, dangerous. The sky above is a pale, washed-out blue. The sun is slightly dimmer than the sun you know, because the solar constant, the amount of energy the sun produces, increases slowly over geological time. But even with a slightly dimmer sun, the heat is oppressive. Because the atmosphere has more carbon dioxide than your time. Not as much as during the Permian-Triassic extinction, but still elevated. Around 1,200 parts per million, compared to 400 in your time. That extra CO2 traps heat, greenhouse effect, and it makes the climate warmer, more humid in some regions, more arid in others. You notice the air feels thin, not drastically, not like high altitude, but noticeably. Oxygen levels in the Triassic atmosphere are around 16 to 18%, compared to 21% in modern times. That's survivable. You can breathe. But if you try to run, you'll tire quickly. Your muscles will burn. Your lungs will strain. This is a low oxygen world, and the animals that live here are adapted to it in ways you're not. You hear a sound, a low grunting bellow from somewhere behind you. You turn, and you see them, a herd of Dicynodonts, Placeras. Barrel-bodied therapsids the size of cows, with beaked mouths and small tusks protruding from their upper jaws. There are maybe 20 of them, moving slowly across the plain, heads down, cropping the tough, fibrous vegetation. These are some of the last surviving therapsids. Their ancestors dominated the Permian. But after the Great Dying, their diversity collapsed. By the late Triassic, only a handful of lineages remain, and Placerias is one of them. They're strange-looking animals, mammal-like, but not mammals. Their legs splay out slightly to the sides, a sprawling gait, though more efficient than a lizard's. Their skin is thick, leathery, probably sparsely covered with hair-like structures, proto-fur. They move with a slow, deliberate waddle, conserving energy in the heat. One of them stops and raises its head, looking in your direction. Its eyes are small, set on the sides of its broad skull. It watches you for a moment, chewing, then loses interest and returns to feeding. You're not a threat, and it's too hot to be alarmed. But then you hear another sound, a hissing, low and continuous, coming from the cluster of cycads to your right. You freeze, because you know what that sound is. You've read about it, seen the fossils, studied the reconstructions, a Crurotarsan, and not a small one. It emerges from the vegetation slowly, head low, body moving with a smooth, predatory grace. Postosuchus. 4 meters of muscle, teeth, and killing intent. Its skin is covered in rectangular, interlocking scales, with larger osteoderms, bony plates, running down its back and tail. Its coloration is mottled brown and tan, camouflage adapted to the arid landscape. But it's the eyes that hold you, forward-facing, binocular vision, the eyes of a predator that judges distance before striking. It's not looking at you, it's looking at the Placerias herd. The Dicynodonts have noticed it too. The nearest ones freeze, then slowly begin to back away, bellowing alarm calls. The herd tightens, adults moving to the outside, younger individuals sheltering in the center. This is a practiced response. They know this danger. They've survived it before. Postosuchus moves closer, still low, still slow. Evaluating. Hunting is costly, energy expensive. Even warm-blooded or near warm-blooded, which Postosuchus probably was, the animal can't afford to waste energy on a failed hunt. It needs a vulnerable target, an isolated individual, a juvenile, an old or injured adult. One of the Placerias at the edge of the herd stumbles slightly, favoring its left foreleg, limping, and Postosuchus sees it. Everything happens fast. Postosuchus lunges forward, rising onto its hind legs, covering the distance in seconds. The Placerias tries to run, but the injured leg buckles. Postosuchus is on it. Jaws clamp onto the Dicynodon's flank. A thrashing struggle. The herd scatters, bellowing, fleeing in all directions. Dust rises, and then it's over. The Placerias is down. Postosuchus has a firm grip. It drags the carcass back toward the cycad thicket, away from the open ground, to feed in relative safety. You've just witnessed a kill, a normal event in the late Triassic. Predator and prey, the ecology of a world dominated by Crurotarsans. But notice what wasn't there. Dinosaurs. You didn't see any, because in this time, in this place, dinosaurs are rare. If you spent days walking across this landscape, you might encounter one. A small theropod, Coelophysis perhaps, skulking in the underbrush, hunting lizards and early mammals. But you'd be more likely to see Crurotarsans, therapsids, rhynchosaurs. The dinosaurs are here, but they're marginal. Background animals in someone else's ecosystem. Now let's jump forward. 20 million years, same location, but it's now the early Jurassic, 200 million years ago. The Triassic-Jurassic extinction has happened, and everything has changed. The heat is still there. Pangaea hasn't broken apart yet, though the rifting has begun. But the landscape looks different. greener. The floodplain is still arid, but the vegetation is denser. More conifers, more cycads. The forests have expanded, and crucially, there's more water. The climate is slightly wetter, more seasonal rainfall. Rivers flow more reliably. You hear sounds, lots of sounds, bellowing, hissing, the thud of heavy footsteps. You turn toward the gallery forest, and you see them. Sauropods, early ones, but unmistakable. Long necks, long tails, massive bodies supported on column-like legs. These are Barapasaurus, or something similar. Not as large as the giants of the late Jurassic, but still impressive. 10 to 15 meters long, several tons in weight. There are 3 of them, moving slowly through the forest, necks reaching up into the conifer branches, stripping foliage. And there, partially hidden in the undergrowth, a theropod, Dilophosaurus. 6 meters long, gracile but powerful, with distinctive paired crests on its skull. It's watching the sauropods, but not hunting them. They're too large, too dangerous. Instead, it's waiting, scavenging perhaps, or hunting smaller prey. This is a dinosaur world now. The Crurotarsans are gone, the terrestrial ones at least, and the dinosaurs have expanded into every niche. Small theropods, large theropods, herbivorous sauropods. Early ornithischians, though they're still rare and small in the early Jurassic. The transition from Triassic to Jurassic, from Crurotarsan dominance to dinosaur dominance, happened in less than 1 million years. Geologically instantaneous. One world died, another was born. And if you could stand at the boundary at that moment 201 million years ago, you'd witness one of the most profound ecological transformations in Earth's history. But what caused the transformation? We've talked about the extinction, the volcanism, the climate change. But let's dig deeper. Let's look at the specific mechanisms, because understanding those mechanisms helps us understand not just the Triassic, but extinctions in general, including the one we're living through right now. The Central Atlantic Magmatic Province eruptions released an estimated 30,000 gigatons of carbon dioxide into the atmosphere over several 100,000 years. For comparison, humans have released about 600 gigatons of CO2 since the Industrial Revolution. So Camp released 50 times more, but over a much longer period. Still, the rate was extraordinary by geological standards. That CO2 drove rapid warming. Global average temperatures increased by 3 to 4 degrees Celsius. But the effects weren't uniform. The poles warmed more than the tropics, reducing the temperature gradient between equator and pole. And that had consequences for ocean circulation, for atmospheric circulation, for rainfall patterns. Some models suggest that the monsoons, the seasonal shifts in wind and precipitation that are crucial for many ecosystems, collapsed or became erratic. Wet seasons failed. Dry seasons extended. Regions that had relied on predictable rainfall patterns suddenly faced droughts lasting years or decades. And the oceans. The oceans absorbed much of the excess CO2, as they always do. But CO2 dissolved in water forms carbonic acid. The ocean pH dropped. Acidification. And anything that built a shell or skeleton from calcium carbonate, which dissolves in acidic water, was in trouble. Corals, mollusks, foraminifera, many went extinct. On land, the combination of heat, drought, and possibly acid rain devastated plant communities. And when plants die, herbivores starve. And when herbivores die, carnivores starve. It's a cascade, a trophic collapse, starting at the bottom and working its way up. But here's the thing. Not all plants died. Not all herbivores, not all carnivores. Some survived. And the question is, which ones? What traits, what characteristics allowed certain species to endure while others perished? For plants, it seems that tolerance to water stress was key. Species with deep root systems, thick cuticles, the ability to survive prolonged drought, these were the survivors. Ferns, which can sporulate and lie dormant, did relatively well. Some conifers, adapted to dry conditions, persisted. But other plant groups, less tolerant, declined or vanished. For herbivores, dietary flexibility was probably crucial. Specialists, animals that fed on specific plants, would have been devastated if their food plants went extinct. Generalists, animals that could eat a variety of plants, had better odds, and smaller animals with lower food requirements were more likely to survive than large ones. For carnivores, the calculus was brutal. If your prey went extinct, you starved. Period. Large apex predators at the top of the food chain are always the most vulnerable during extinctions because they depend on the entire ecosystem below them remaining intact. When that ecosystem collapses, they collapse with it. And this may be why the crurotarsans died and the dinosaurs survived. The large crurotarsan predators, Postosuchus, Saurosuchus, were apex predators, specialists. They hunted large prey. When those prey populations crashed during the extinction, the predators had nothing to eat, and they died. Dinosaurs, being smaller and possibly more generalist in their diets, may have been able to subsist on whatever was available. Insects, small vertebrates, carrion, plants even for some species. They survived the bottleneck, and when conditions improved, when plant productivity recovered, they were the ones left standing. But this is speculation. Educated, evidence-based speculation, but speculation nonetheless. The fossil record from the Triassic-Jurassic boundary is frustratingly incomplete in many regions. We have snapshots, isolated moments. But the full picture, the day-by-day, year-by-year progression of the extinction is lost to time. What we do know is the outcome. Crurotarsans gone, dinosaurs ascendant, and the Jurassic, the age that followed, was utterly dominated by dinosaurs in a way the Triassic never was. But let's return to the Triassic itself, because there's one event we haven't discussed yet. An event that happened in the middle of the Triassic, long before the end Triassic extinction. An event that may have been crucial to the rise of the dinosaurs, even though it didn't directly cause their dominance. The Carnian Pluvial Episode. It's a terrible name. Sounds like a minor geological footnote. But it was anything but. It was one of the strangest climate events in Earth's history. And it happened right when dinosaurs were first evolving. 234 million years ago, Middle Triassic. The climate of Pangaea, which had been hot and dry for millions of years, suddenly flipped. It became wet, very wet. For 2 million years, the supercontinent was drenched in rain. Mega monsoons. Rivers swelled. Lakes formed in basins that had been dry for eons. Forests expanded. Wetlands covered vast areas. We know this from geology, from sedimentary rocks that show a sudden shift from arid, desert-like conditions to humid, swamp-like conditions, from fossil soils that preserve evidence of increased rainfall, from the distribution of certain plant fossils that only grow in wet environments. What caused it? The leading hypothesis involves volcanism. Again, specifically the eruption of the Wrangell terrain, a large igneous province in what is now British Columbia and Alaska. The eruptions released CO2, triggering warming, which increased evaporation from the oceans, which increased rainfall. A feedback loop. Greenhouse warming causing increased precipitation. And this wet period, this Carnian pluvial episode, coincides almost exactly with the first appearance and early diversification of dinosaurs. Is that a coincidence? Maybe, but maybe not. Here's a hypothesis. Before the Carnian pluvial episode, during the hot, dry conditions of the early and early Middle Triassic, archosaurs were diversifying, but slowly. The environment was harsh. Resources were limited. Ecological niches were occupied by therapsids and other groups. The Crurotarsans, being larger and already established, dominated. Then the climate shifted. Suddenly, there was more water, more plant growth, more insects, more small vertebrates, new habitats, swamps, riverine forests. And new habitats mean new ecological opportunities. Dinosaurs, which were small and probably adapted to more humid, vegetated environments, may have thrived during the Carnian pluvial episode. They may have diversified, experimented with new body plans, new diets, new behaviors. While the Crurotarsans, adapted to drier conditions, may have been less able to exploit the new opportunities. The fossil record supports this, somewhat. The first diverse dinosaur assemblages appear in the late Carnian, during and immediately after the pluvial episode. The Ischigualasto Formation in Argentina, one of the most important dinosaur-bearing formations of the Triassic, dates to this time. And it contains multiple dinosaur species, representing different lineages, different body sizes, different diets. So the Carnian pluvial episode may have been the trigger, the event that allowed dinosaurs to start diversifying. But it didn't make them dominant. After the episode ended, after the climate dried out again, the Crurotarsans came back strong. They continued to dominate for another 30 million years. It took the end Triassic extinction to finally clear the field, to remove the competition, to give the dinosaurs their chance. And they took it. Let's talk numbers for a moment. Because numbers help us understand just how dramatic the shift was. In late Triassic fossil assemblages, before the extinction, dinosaurs typically make up less than 10% of large vertebrate fossils, often less than 5%. The rest are Crurotarsans, therapsids, rhynchosaurs, and other groups. In early Jurassic fossil assemblages, after the extinction, dinosaurs make up 70 to 90% of large vertebrate fossils. The other groups are gone or drastically reduced. The ecosystem flipped. And it's not just abundance, it's diversity. In the late Triassic, there are maybe a dozen well-defined dinosaur genera. By the Middle Jurassic, there are dozens. By the late Jurassic, over 100. The diversification was explosive. And it wasn't just on land. In the air, pterosaurs, which are not dinosaurs but close relatives, diversified enormously during the Jurassic. And in the oceans, while dinosaurs never became fully aquatic, other reptile groups, ichthyosaurs and plesiosaurs, flourished. The Jurassic was a world of reptiles, dominated by archosaurs and their relatives in a way the Triassic never was. The Triassic was a transition, a recovery, a competition between multiple groups. The Jurassic was a dynasty. The age of dinosaurs had truly begun. But here's the question that haunts paleontologists. What if the end Triassic extinction hadn't happened? What if the camp eruptions had been smaller, or in a different location, or mistimed? What if the Crurotarsans had survived? Would the dinosaurs have ever become dominant? Or would they have remained marginal, rare, overshadowed by Crurotarsans for the rest of the Mesozoic? We can't know, not for certain. But the evidence suggests that without the extinction, dinosaurs would have stayed in the background, because for 30 million years they tried to compete, and they lost. It was only when the competition was removed that they succeeded. And that tells us something profound about evolution. About success. About the nature of life itself. Evolution is not progressive. It doesn't move towards some goal. It doesn't reward the best in an absolute sense. It rewards what works right now in the current environment. And when the environment changes catastrophically, when a mass extinction occurs, all bets are off. The previous winners can become losers, and the previous losers can become winners. Dinosaurs were losers in the Triassic, by any measure. They were rare, small, outcompeted. If you were a betting person in the late Triassic, you would not have bet on dinosaurs. You would have bet on Crurotarsans. They were bigger, more diverse, more successful. They had been dominant for 40 million years. They showed every sign of continuing to dominate. But then the extinction happened, and the Crurotarsans, for reasons we still don't fully understand, couldn't survive it, and the dinosaurs could. And that changed everything. This is the contingency of history, the role of chance, luck, accident. It's uncomfortable because it means that the world we know, the ecosystems we study, the species we see, including ourselves, are not the inevitable products of evolutionary progress. They're the products of a long series of contingent events, different outcomes. If the end Triassic extinction had been slightly different, we might live in a world where the descendants of Postosuchus are the dominant large land animals, where Crurotarsans, not dinosaurs, evolved gigantism, where birds never evolved because theropod dinosaurs never became dominant enough to develop flight. And if the Cretaceous-Paleogene extinction, the asteroid 66 million years ago, hadn't happened, we certainly wouldn't be here. Because mammals, our ancestors, were small, nocturnal, marginal creatures during the Mesozoic, overshadowed by dinosaurs the same way dinosaurs were overshadowed by Crurotarsans in the Triassic. It took the extinction of the non-avian dinosaurs for mammals to get their chance, to diversify, to grow large, to eventually produce primates, hominids, humans. We are the beneficiaries of catastrophe, just like the dinosaurs. Our existence depends on extinctions that killed other, more successful groups. And if that doesn't give you perspective on humanity's place in nature, nothing will. But this isn't just a philosophical point. It has practical implications. Because we're living through a mass extinction right now, the sixth mass extinction, the Anthropocene extinction, caused by us, by human activity, habitat destruction, climate change, pollution, overhunting, invasive species. Species are going extinct at rates 100 to 1,000 times higher than the background rate. Some estimates suggest we've already lost more than half of the world's wildlife in the past 50 years. And the rate is accelerating. If current trends continue, we could lose a significant fraction of Earth's biodiversity within the next century. Not just species, but entire ecosystems, coral reefs, rainforests, grasslands, gone or irreversibly altered. And the lesson from the Triassic is clear. Extinctions don't just remove species, they reshape ecosystems. They change which groups succeed and which groups fail. They reset the game. Right now, we're at the top. Humans are the dominant species. We control most of the planet's surface. We appropriate a huge fraction of its primary productivity. We're the apex predator, the apex herbivore, the apex everything. But dominance is temporary. The Crurotarsans were dominant for 40 million years. Then they went extinct. Dinosaurs were dominant for 165 million years. Then most of them went extinct. Mammals have been dominant for 66 million years. And we're causing an extinction that we may not survive. Because here's the thing. When you cause a mass extinction, you don't get to choose who survives. You can't exempt yourself. Extinctions are chaotic, unpredictable. They kill specialists. They kill dominance. They kill anything that can't adapt quickly to rapidly changing conditions. And humans, for all our technology, are specialists. We depend on agriculture, on stable climates, on predictable rainfall, on ecosystems that provide services we take for granted: pollination, water filtration, soil formation. When those ecosystems collapse, we collapse with them. We like to think we're different, that we can engineer our way out of any problem, that our intelligence makes us immune to the forces that govern other species. But the fossil record says otherwise. Intelligence doesn't protect you from extinction. Dinosaurs had bird-level intelligence, some of them. Didn't save them from the asteroid. Crurotarsans were successful for 40 million years. Didn't save them from the Triassic-Jurassic extinction. Survival depends on adaptability, on being in the right place with the right traits when disaster strikes. And we don't know if we have those traits. We won't know until the disaster happens. And by then, it's too late. The Triassic teaches us humility. It shows us that success is not destiny, that dominance is not permanence, that the winners can lose and the losers can win if the world changes fast enough. And the world is changing, faster than at any point in human history, faster in some ways than during the Triassic-Jurassic extinction. We're running the same experiment the planet ran 201 million years ago, dumping greenhouse gases into the atmosphere, warming the climate, acidifying the oceans, disrupting ecosystems. The outcome then was mass extinction followed by 165 million years of dinosaur dominance. What will the outcome be now? We don't know. But if history is any guide, the groups that thrive after our extinction event, if there is one, won't be the ones that are dominant now. They'll be the small, flexible, adaptable ones, the ones we don't notice, the rats and the cockroaches and the weeds, just like the dinosaurs in the Triassic, small, marginal, waiting. But let's step back from the existential dread for a moment and return to the science. Because there's another piece of the Triassic puzzle we haven't fully explored: the animals themselves, what they actually were, how they lived, what their world felt like from the inside. We've talked about Crurotarsans as a group, but let's get specific. Let's meet some individuals, because the Triassic produced some of the strangest, most alien-looking creatures ever to walk the earth. Animals that defy our expectations of what reptiles should look like, what predators should look like, what life should look like. Start with the Ophidia, discovered in New Mexico in 2006. When paleontologists first saw the skeleton, they thought it was a dinosaur, specifically an ornithomimosaur, a group of ostrich-like theropod dinosaurs from the Cretaceous. The resemblance was striking. Long neck, small head, toothless beak. long legs built for running, reduced forelimbs. Even the proportions were similar. But when they analyzed the skull in detail, they realized it wasn't a dinosaur at all. It was a Crurotarsan, a relative of crocodiles. Iphygia had independently evolved a body plan almost identical to ornithomimosaurs. Same lifestyle, probably herbivorous or omnivorous. Same adaptations for speed, same basic shape, but completely different evolutionary origin. This is convergent evolution at its most extreme. Two unrelated groups, separated by 150 million years, evolving nearly identical solutions to the same ecological problem: how to be a fast, long-legged herbivore in an open environment. And Iphygia wasn't alone. There were other Crurotarsans that looked like dinosaurs. Shuvosaurus, another beaked bipedal form. Poposaurus, similar body plan. These animals were Crurotarsan dinosaur mimics, living in the same environments, eating similar foods, moving in similar ways. If you saw one running across the Triassic plains, you'd swear it was a dinosaur. But it wasn't. Why does this matter? Because it shows that the dinosaur body plan, the upright bipedal form, the long legs, the specialized adaptations, wasn't unique to dinosaurs. Crurotarsans could do it too. They were exploring the same evolutionary space, and they were doing it successfully. Which raises the question again. If Crurotarsans could evolve dinosaur-like forms, if they were just as capable of adopting those body plans, why didn't they persist? Why did the actual dinosaurs outlast them? We keep coming back to the extinction, to luck, to contingency, because the Crurotarsans weren't inferior, they were different. And difference in evolution isn't about better or worse, it's about fit. How well you match your environment at a specific moment in time. The Crurotarsans fit the Triassic, the dinosaurs fit the Jurassic. The transition between those two worlds, the extinction, was the filter, and only the dinosaurs passed through. Now let's talk about something truly bizarre: Triassic marine life. Because while we've focused on land, the oceans were undergoing their own strange evolutionary experiments. The Permian-Triassic extinction had devastated marine ecosystems even more thoroughly than terrestrial ones. 96% of marine species extinct, coral reefs gone, trilobites extinct, most brachiopods gone. The ocean was a graveyard, but life, as always, recovered. And it recovered in unexpected ways. In the early Triassic, the oceans were dominated by disaster taxa, simple organisms, generalists. But by the Middle Triassic, complex marine ecosystems were rebuilding, and some of the animals doing the rebuilding were reptiles, land animals that had returned to the sea, ichthyosaurs, fish lizards. These were among the most successful marine reptiles of the Mesozoic, and they appeared in the early Triassic, almost immediately after the extinction. The earliest forms were small, eel-like, probably still spending time on land. But within a few million years, they were fully aquatic, streamlined, fast, dolphin-like, though they weren't related to dolphins. They were reptiles, diapsids, distant cousins of the archosaurs. By the Middle and Late Triassic, ichthyosaurs had evolved into apex predators. Shonisaurus from Nevada reached lengths of 15 meters, 50 feet. Among the largest marine reptiles ever. It had enormous eyes, the largest of any vertebrate, adapted for hunting in deep, dark water. It probably fed on squid and fish, diving to depths of hundreds of meters. But ichthyosaurs weren't alone. There were other marine reptile groups: nothosaurs, placodonts, thalatosaurs, each experimenting with different body plans, different diets, different strategies. Placodonts are particularly strange. Imagine a reptile the size of a sea lion, but with a turtle-like shell and massive, flat, crushing teeth. That's a placodont. They fed on shellfish, clams, brachiopods, anything with a hard shell. Their teeth were perfectly adapted for crushing. Broad, flat, powerful jaw muscles. They dive to the seafloor, pry shellfish off rocks, crush them, swallow the soft tissue, spit out the shell fragments. Some placodonts, like Henodus, evolved to look almost exactly like turtles. Flat shells, beaked mouths, even similar proportions. But they weren't turtles. Turtles are a completely different lineage. This was, again, convergent evolution. Two unrelated groups arriving at the same solution. And then there were the nothosaurs, long-necked, long-tailed marine reptiles that looked vaguely like plesiosaurs, the famous marine reptiles of the Jurassic and Cretaceous. But nothosaurs weren't plesiosaurs. They were an earlier experiment. A different branch of the reptile family tree, trying out the long-neck paddle flipper body plan. They were successful for a time, but most went extinct at the end of the Triassic, replaced in the Jurassic by actual plesiosaurs, which evolved from a different ancestor. The pattern here is clear. The Triassic was a time of experimentation. Life was trying everything. Multiple groups independently evolving similar solutions. Many of those experiments were successful for a time, but few lasted beyond the Triassic. The end Triassic extinction pruned away most of the diversity, leaving only a few lineages to carry forward into the Jurassic. It's like evolution was running multiple beta tests simultaneously. Most failed. A few succeeded spectacularly, but you couldn't predict which would be which until the test ended. Let's zoom in on another specific animal, because individual species can teach us things that broad patterns can't. Tanystropheus. This is one of the weirdest reptiles ever discovered, and that's saying something in the Triassic, a period full of weird reptiles. Tanystropheus was about 6 meters long, 20 feet, but half of that length, 3 meters, was neck. Just neck. An absurdly long neck, longer proportionally than any sauropod dinosaur, supported by only 12 or 13 elongated vertebrae. Each vertebra was stretched out like a piece of taffy, creating a neck that was stiff, inflexible, almost like a fishing rod. For over a century after its discovery, paleontologists argued about what Tanystropheus was, how it lived, what it ate. Some thought it was terrestrial, using its long neck to reach vegetation high in trees. Others thought it was aquatic, using the neck like a snorkel. Still others suggested it was a coastal wader, using the neck to reach prey in shallow water without getting its body wet. In 2020, a study using CT scanning and microscopic analysis of the bones finally settled the debate. Tanystropheus was aquatic. Fully aquatic. It lived in the ocean, hunting fish and squid. The long neck was a fishing apparatus. The animal would hide its body, keep it motionless, and strike with the neck like a spear, impaling prey with its sharp teeth. But here's the strange part. Tanystropheus had no special adaptations for swimming. No flippers, no paddle-like tail, just normal limbs. It probably swam awkwardly, inefficiently, which suggests it spent most of its time floating or drifting, using ocean currents, conserving energy. The neck was the primary tool. The body just had to not sink. This is a weird way to be a marine predator. No modern animal does anything like this, but it worked. Tanystropheus fossils are found across Europe and the Middle East, indicating it was widespread and successful for millions of years during the Middle Triassic. And then it went extinct. Not at the end Triassic extinction, but earlier in the Carnian, possibly during or after the Carnian pluvial episode. Environmental change, ecosystems shifting, and Tanystropheus, specialized for a specific niche, couldn't adapt. Gone. The Triassic is full of stories like this. Successful animals, unusual animals, animals that dominated their ecosystems for millions of years, then disappeared, leaving no descendants, no evolutionary legacy, just fossils. And that brings us to one of the most important concepts in paleontology: the concept of total extinction versus phylogenetic survival. When we say a group went extinct, we can mean two different things. We can mean that all members of the group died, leaving no descendants. That's total extinction. Or we can mean that the group as a whole disappeared, but one or more lineages within the group survived and evolved into something else. That's phylogenetic survival. For example, non-avian dinosaurs went totally extinct 66 million years ago. But avian dinosaurs, birds, survived. So dinosaurs as a whole show phylogenetic survival. The group persists in modified form. Crurotarsans, on the other hand, show a mix. The terrestrial crurotarsans, the bipedal predators, the armored herbivores, went totally extinct at the end of the Triassic. No descendants. But some aquatic and semi-aquatic crurotarsans survived, and their descendants are still alive today. Crocodiles, alligators, gharials, caimans. So modern crocodilians are the sole surviving lineage of a group that once dominated the planet. They're the last remnant of the Crurotarsan Empire. And interestingly, they survived by staying in the water, by not competing directly with dinosaurs on land, by occupying a niche, the large aquatic predator niche that dinosaurs never successfully invaded. This tells us something about survival strategies. Sometimes the way to survive a mass extinction is to stay out of the way, to occupy a niche that's less affected by the extinction's causes. Aquatic environments may have buffered some of the effects of the end Triassic climate change. Temperature fluctuations are less extreme in water. Food webs may have been more stable. And so aquatic crurotarsans survived while their terrestrial relatives perished. The same pattern holds for other groups. Therapsids were devastated by the end Permian extinction. But one lineage, small, nocturnal, insectivorous forms, survived, and their descendants became mammals. The therapsids didn't totally go extinct. They evolved into us. Phylogenetic survival. Understanding this distinction is crucial because it tells us that extinction isn't necessarily the end. It's a filter. A severe one, yes. But some lineages pass through. And those that do often undergo rapid evolutionary change in the aftermath, exploiting the empty niches left by the extinct groups. This is adaptive radiation, and it's happened repeatedly throughout Earth's history. After every major extinction, the survivors diversify, explode into new forms, fill the gaps. The Triassic-Jurassic extinction was followed by the adaptive radiation of dinosaurs. The Cretaceous-Paleogene extinction was followed by the adaptive radiation of mammals. And the Permian-Triassic extinction was followed by the adaptive radiation of archosaurs, including both dinosaurs and crurotarsans. Extinctions are destructive, but they're also creative. They clear the board. They create opportunities. They allow evolution to try new things. Without extinctions, we'd have stagnation. The same groups persisting indefinitely, filling all available niches, preventing newcomers from establishing themselves. It's a harsh way to drive innovation, but it's the way life works, has always worked. Extinction and radiation, death and rebirth. The cycle has been running for over 3 billion years, and it shows no sign of stopping. So what does the Triassic tell us about this cycle? It tells us that recovery from mass extinction is slow. It took 10 million years after the Permian-Triassic extinction for ecosystems to regain even moderate diversity. It tells us that the immediate aftermath of an extinction is dominated by generalists and disaster taxa. It tells us that the groups that eventually come to dominate are often not the ones that dominated before the extinction. And crucially, it tells us that predicting winners and losers is nearly impossible, because the winners are determined by the specific circumstances of the extinction, which are unpredictable. If you were a scientist in the Middle Triassic, watching crurotarsans and dinosaurs evolving side by side, you could not have predicted that dinosaurs would inherit the Earth. All the evidence pointed the other way. Crurotarsans were more successful by every measure, but they lost. Because the specific circumstances of the end Triassic extinction happened to favor dinosaurs, or at least didn't kill them. Luck, contingency, the roll of the dice. That's what determined the fate of the Mesozoic. And by extension, our fate. Because if dinosaurs hadn't survived, mammals might never have gotten their chance, and humans might never have evolved. We are the products of chance events in deep time, and that's simultaneously humbling and terrifying. Let's talk about one more aspect of the Triassic that often gets overlooked: the climate. We've mentioned it in passing: the heat, the aridity, the Carnian pluvial episode. But let's really dig into what Triassic climate was like and why it mattered. Pangaea was a climatic nightmare, and that's not an exaggeration. Supercontinents create extreme climates because of their size and geometry. Here's why. Oceans moderate temperature. Water has a high heat capacity, meaning it takes a lot of energy to change its temperature. Coastal regions benefit from this. The ocean absorbs heat in summer and releases it in winter, keeping temperatures relatively stable. But continental interiors, far from any ocean, don't have this moderating influence. They get hot in summer and cold in winter, extremely hot and extremely cold. Pangaea was the largest supercontinent in the last 500 million years. At its maximum extent, it covered nearly a third of the planet's surface, and much of its interior was thousands of kilometers from the nearest ocean. That meant extreme continentality, extreme temperature swings, and extreme aridity. Because here's the other problem with supercontinents: they disrupt atmospheric circulation. On modern Earth, we have multiple ocean basins: the Atlantic, the Pacific, the Indian Ocean, and these basins drive weather patterns. Moisture evaporates from the oceans, moves over land, falls as rain. The system is distributed, regional. But on Pangaea, there was only one major ocean, Panthalassa, the super ocean, and most of its moisture never reached the continental interior. It fell along the coasts. By the time air masses moved inland, they'd already lost their moisture. The interior was a rain shadow, a desert. The largest desert in Earth's history. Computer models of Triassic climate show that vast swaths of Pangaea's interior received less than 25 centimeters of rain per year. That's Sahara desert levels. And remember, this wasn't just a small desert. This was a desert the size of Asia for tens of millions of years. And it wasn't just dry, it was hot. CO2 levels in the Triassic were elevated, as we've discussed. That meant greenhouse warming. Global average temperatures were probably 5 to 10 degrees Celsius higher than today. But in the continental interior, away from the ocean's moderating influence, temperatures were even higher. Summer highs in the tropics may have regularly exceeded 50 degrees Celsius. That's approaching the limit of vertebrate survival. Most modern reptiles, even desert-adapted ones, can't survive prolonged exposure to temperatures above 45 degrees. Their proteins denature. Their cells die. They have to seek shade, burrow underground, or estivate, enter a state of dormancy. So how did Triassic animals survive? Several strategies. First, many of them were probably restricted to more temperate latitudes, avoiding the tropics entirely. Fossil evidence supports this. Triassic fossil sites at mid-latitudes, 30 to 45 degrees north or south, are far more diverse than those near the equator. The tropics may have been a dead zone for much of the year. Second, animals that did live in hot, dry regions probably had behavioral adaptations: nocturnal activity, burrowing, seasonal migration, following water sources. We can infer some of this from trackways and burrow fossils, but much of it is guesswork. Third, physiological adaptations. Some Triassic reptiles may have had better heat tolerance than modern ones, more efficient cooling mechanisms, higher thermal maxima. We can't know for certain without living animals to test, but the fact that large active predators like Postosuchus lived in equatorial regions suggests they had some way of dealing with the heat. And fourth, the Triassic climate wasn't uniformly hot and dry. There were regional variations. Coastal areas were more humid. Higher latitudes were cooler. Mountainous regions had rainfall and temperate conditions. And there were rivers, fed by distant mountains, that created ribbons of habitability through otherwise inhospitable terrain. These riparian corridors, river valleys with reliable water and vegetation, were crucial. They were highways for animal movement, refugia during droughts, hotspots of biodiversity. Many of the richest Triassic fossil sites are ancient river deposits, because that's where the animals were. But here's the thing. Even these refugia were vulnerable, because the Triassic climate was unstable. It fluctuated wildly, on timescales of thousands to millions of years, driven by volcanic activity, by orbital variations, by changes in ocean circulation, and these fluctuations created stress. Populations expanded during good times, contracted during bad times. Some species went locally extinct, recolonized later. Others went fully extinct, unable to survive the bottlenecks. This climate instability may have been a driving force behind Triassic evolution. Constant environmental stress favoring adaptability over specialization, favoring generalists that could tolerate a wide range of conditions. And this, again, may be why dinosaurs survived the end Triassic extinction. They were stress-tolerant generalists, while Crurotarsans, more specialized, more finely tuned to specific conditions, couldn't cope when those conditions changed abruptly. It's an appealing hypothesis. But as with everything about the end Triassic extinction, we can't be certain. The evidence is suggestive, but not conclusive. and science demands we acknowledge uncertainty. What we can say with confidence is that the Triassic was a period of extreme climates, ecological instability, and evolutionary experimentation. A time when the planet was recovering from catastrophe and setting the stage for the age of dinosaurs. A transitional period, a bridge between the Paleozoic world of therapsids and amphibians and the Mesozoic world of dinosaurs and mammals. And crucially, a reminder that Earth's climate is not static. It never has been. It changes, sometimes gradually, sometimes abruptly. And those changes drive evolution, drive extinction, drive the entire history of life. We're living through rapid climate change right now, anthropogenic climate change, caused by us. And the Triassic shows us what happens when climate changes faster than evolution can adapt. Extinctions, ecosystem collapse, replacement of old groups by new ones. The difference is that this time we're causing it, which means we have agency. We can slow it, stop it, mitigate it. The question is whether we will, whether we can overcome our political divisions, our economic inertia, our psychological denial, and actually do what needs to be done. The Triassic can't answer that question, but it can warn us. It can show us the consequences of ignoring climate change, of assuming that things will just work out. Because in the Triassic, things didn't just work out. 76% of species went extinct. Ecosystems took millions of years to recover. The world that emerged was fundamentally different from the world that preceded it. Is that what we want? A world where most of what we know is gone, where ecosystems have collapsed and something new, something alien has taken their place, where humans, if they survive at all, are reduced to a marginal remnant, clinging to existence in whatever refugia remain habitable. That's the trajectory we're on. The Triassic shows us it's possible. It's happened before, and it can happen again. But it also shows us something else. That life is resilient, that even after the worst catastrophes, even after 96% of species go extinct, life bounces back, slowly, painfully, but it bounces back. New forms evolve, new ecosystems establish, the planet heals. Just not on timescales that matter to us. Not on timescales that matter to human civilization. We're talking millions of years, and we don't have millions of years. We have decades, maybe a century, to stabilize the climate, to preserve biodiversity, to ensure that our species and the ecosystems we depend on survive. The Triassic is a warning, but it's also a lesson in humility, in understanding our place in the vast sweep of Earth's history. We're not special. We're not exempt from the forces that govern all life. We're just another species, highly successful right now, but ultimately mortal, vulnerable, subject to the same evolutionary and ecological laws as every other organism that's ever lived. The dinosaurs rose and fell. The Crurotarsans rose and fell. The therapsids rose and fell. Every group that's ever dominated this planet has eventually been replaced. And we will be too. The only question is when, and whether we go out with a whimper or a bang, whether we take most of the planet's biodiversity with us, or whether we manage to leave something intact for whatever comes after. The Triassic suggests we won't leave much, that mass extinctions are indiscriminate, that when civilizations collapse, they take ecosystems with them. But maybe we can be different. Maybe, knowing what we know, understanding what we understand, we can break the pattern. Maybe we can be the first dominant species to voluntarily limit our impact. to choose sustainability over expansion, to survive by adapting rather than by exploiting until there's nothing left to exploit. Maybe. But history, both human and geological, suggests otherwise. The Triassic is over. It ended 201 million years ago, but its lessons remain. Written in stone, in the fossils of crurotarsans and early dinosaurs, in the geochemistry of ancient rocks, in the sediments that record climate change and extinction, and those lessons are clear. Dominance is temporary, survival is uncertain, and luck matters more than we'd like to admit. The dinosaurs got lucky, twice. Once during the Triassic-Jurassic extinction, when they survived and their competitors didn't. And once during the 165 million years that followed, when no other major extinction removed them. Until finally, inevitably, their luck ran out. Will ours? Let's return to the Triassic one more time. Not to the desert, not to the fossils, but to the moment. The specific instant when the world pivoted, when one dynasty ended and another began, 201 million years ago. The Triassic-Jurassic boundary, ground zero. Imagine you're standing in what will become the Fundy Basin on the east coast of North America. But right now, there is no Atlantic Ocean. Pangaea is splitting, but slowly. The rift that will become the Atlantic is just beginning to open. And along that rift, the Earth is tearing itself apart. You feel it before you see it. A low rumble, deep and constant, like distant thunder that never stops. The ground vibrates beneath your feet. And then, on the horizon, a glow. Red, angry, growing brighter. A fissure has opened in the crust. Magma rising from the mantle is forcing its way to the surface. Not a single volcano, but a curtain of fire. A wall of lava fountains stretching for kilometers. The camp eruptions have begun. The lava doesn't flow like water. It's too viscous, too thick. It oozes, creeps forward at walking pace. But there's so much of it. Rivers of molten rock, hundreds of meters wide, spreading across the landscape. Everything in their path burns. Trees, vegetation, animals that can't flee fast enough. The heat is unbearable even from a distance. Kilometers away, the air shimmers. Your skin blisters. And the gases. Oh, the gases. Sulfur dioxide, pouring from the fissures in visible clouds. Yellow, choking. It reacts with moisture in the atmosphere, forming sulfuric acid. Acid rain begins to fall within hours. The vegetation that survived the lava dies from the rain. Lakes acidify. Rivers become poisonous. Carbon dioxide, invisible but deadly, accumulates. The greenhouse effect kicks in immediately. Temperatures begin to rise, not gradually, not over centuries, over years, decades. A spike so rapid that ecosystems can't adapt, can't migrate fast enough. Plants wilt. Herbivores starve. Carnivores, losing their prey, follow. This goes on for hundreds of thousands of years. The eruptions aren't continuous, but they're frequent. Every few thousand years, new fissures open. More lava, more gas. The planet is wounded, and the wound won't heal. In the oceans, the effects are catastrophic. The excess CO2 dissolves into seawater, forming carbonic acid. Ocean pH drops. Anything with a calcium carbonate shell finds it increasingly difficult to maintain that shell. It starts to dissolve. Corals die. Mollusks struggle. Entire reef systems collapse. And the warmth. The ocean's surface warms by 3, 4, 5 degrees. Thermal stratification increases. The warm surface water stops mixing with deeper, cooler water. oxygen can't reach the depths. Anoxic zones expand. Dead zones, where nothing can live, spread across the ocean floor. On land, the large animals die first. The apex predators, Postosuchus, Saurosuchus, Phaseolasuchus. They need enormous amounts of food to sustain their bulk. But their prey, the large herbivores, are dying. The plants they depend on are dying. The food web collapses from the bottom up. The predators, starving, turn on each other. Cannibalism becomes common. But it's not enough. One by one, they die, and their lineages go extinct. The crurotarsan herbivores, the atosaurs, fare no better. They're specialists adapted to specific plant types. When those plants die, they have no alternatives. They can't digest the new vegetation that springs up in disturbed environments. Ferns, opportunistic weeds, they starve amid plenty. The rhynchosaurs, so abundant for tens of millions of years, vanish. Completely. Every species, every lineage, gone. Their specialized teeth, perfect for grinding tough Triassic vegetation, are useless in the Jurassic world that follows. And the dinosaurs? They survive. Not all of them. Some dinosaur lineages go extinct, but enough survive. The small ones, the generalists, the ones that can eat insects, plants, carrion, whatever's available. The ones with lower metabolic demands, the ones that can tolerate heat and low oxygen and environmental stress. They survive. And when the eruptions finally stop, when the climate begins to stabilize, when plants start to recover and ecosystems begin to rebuild, the dinosaurs are there, waiting. And there's no competition, no crurotarsans, no therapsids, no rhynchosaurs. The niches are empty, and the dinosaurs fill them, rapidly, explosively. Within 10 million years, the Jurassic fauna is in place. Dinosaurs as apex predators, dinosaurs as herbivores. Dinosaurs in every size class, every habitat, every ecological role that matters. They didn't win through superiority, they won through survival. And that's the lesson. That's what the Triassic teaches us, again and again. Survival is what matters. Not who's strongest, not who's fastest, not who's smartest, who survives the catastrophe. That's who inherits the future. And here's the terrifying part. We can't predict who that will be. Because the factors that determine survival during a mass extinction are specific to that extinction. What worked during the Permian-Triassic extinction didn't work during the Triassic-Jurassic. What worked during the Cretaceous-Paleogene won't work during the next one. Each extinction is unique. Each one selects for different traits, different strategies, different accidents of geography and timing and biology. So when we ask, what would survive a modern mass extinction? The honest answer is, we don't know. We can make educated guesses, small animals, generalists, things that can tolerate a wide range of conditions, things with low metabolic demands. But we can't be certain, because extinction is chaotic, unpredictable, contingent. And humans? Are we small? No. Are we generalists? Somewhat. But we're also highly dependent on agriculture, which is specialist. Can we tolerate a wide range of conditions? With technology, yes. Without it, no. Do we have low metabolic demands? Absolutely not. Humans are energy-intensive organisms living in energy-intensive societies. We're vulnerable, more vulnerable than we'd like to admit. And the Triassic shows us what happens to dominant species when the world changes faster than they can adapt. They go extinct, no matter how successful they were before, no matter how long they dominated. When the environment shifts beyond their tolerance limits, they die. The Crurotarsans dominated for 40 million years. Then they died. Non-avian dinosaurs dominated for 165 million years. Then they died. Mammals have dominated for 66 million years. And we're next. Not might be next, are next. It's just a question of when, and whether we cause our own extinction through climate change and ecosystem destruction and resource depletion, or whether it's caused by something external, an asteroid or a supervolcano or a gamma ray burst, doesn't really matter. The outcome is the same. We're not exempt from the forces that govern all life. We're not special. We're just another species, highly successful right now, but ultimately temporary. That's the existential lesson of the Triassic. Dominance is an illusion. Permanence is a fantasy. Every species, every lineage, every kingdom is temporary. Holding the throne until something, a catastrophe or a competitor or just bad luck, removes them. We've been holding the throne for maybe 300,000 years, depending on how you define Homo sapiens. That's nothing. A blink. The dinosaurs held it for 165 million years, and it didn't save them. Why would it save us? But here's the other lesson, the hopeful one. Life persists. Not individual species, not individual lineages, but life itself. The phenomenon, the process, the chemical reaction that started 3.5 billion years ago and hasn't stopped. The Triassic shows us this too. After the worst extinction in history, the Permian Triassic, life recovered. Slowly, painfully, but it recovered. New forms evolved, new ecosystems established, the planet healed. And the Mesozoic that followed was, in many ways, more diverse, more spectacular than the Paleozoic that preceded it. So, if humans go extinct, life will continue. New species will evolve. New forms will arise. And in a few million years, maybe 10 million, maybe 50, Earth will be just as vibrant and diverse as it was before. More so, perhaps. We won't be here to see it, but it will happen. Because that's what life does. It adapts, it evolves, it fills empty niches, it exploits new opportunities, it never stops. The Triassic was a time of endings and beginnings. The end of the Crurotarsans, the beginning of the dinosaurs, the end of one world, the beginning of another. And in that transition, in that moment of catastrophe and opportunity, we see the fundamental pattern of life on Earth. Destruction and creation, death and birth, extinction and radiation. The cycle repeats, has repeated for over 3 billion years, will continue to repeat long after we're gone. And maybe that's okay. Maybe that's how it should be. Because if life never changed, if dominant species never fell and new ones never rose, evolution would stagnate. We'd be stuck in the Paleozoic, or the Proterozoic, or even earlier. The same organisms persisting indefinitely, filling the same niches, doing the same things. Extinctions, as terrible as they are, drive innovation. They clear the board. They create space for experimentation. They allow evolution to try new things. Without the Permian Triassic extinction, archosaurs might never have diversified. Without the Triassic-Jurassic extinction, dinosaurs might never have dominated. Without the Cretaceous-Paleogene extinction, mammals might never have evolved into us. Every catastrophe is an opportunity, not for the species that die. For them, it's the end. But for the survivors, for the species that happen to have the right traits at the right time, it's a beginning, a chance to inherit a world, to diversify, to become something new. The dinosaurs got that chance, twice, and they made the most of it. For 165 million years, they were the most successful large animals on Earth. They evolved into forms we can barely imagine. Sauropods the size of buildings. Theropods with brains as complex as modern birds. Because, of course, modern birds are theropods. The dinosaurs are still here, still successful, still evolving. The dinosaurs didn't fail. The non-avian lineages failed, yes. But the lineage as a whole persists. In every sparrow and crow and eagle, in every chicken and ostrich and penguin, 10,000 species of living dinosaurs thriving on every continent in every environment. So maybe the question isn't, why did the dinosaurs go extinct? Maybe the question is, why did birds survive when the other dinosaurs didn't? And the answer, again, is luck and timing and specific adaptations. Birds were small. They could fly. They had high metabolic rates, but low absolute energy demands because of their size. They could eat seeds, which survived the Cretaceous-Paleogene extinction better than living plants. They could disperse widely, colonizing new areas as old ones became uninhabitable. They survived, and they inherited a world, the Cenozoic, the age of mammals, yes, but also the age of birds. And they're doing fine, better than fine. They're one of the most diverse and successful groups of vertebrates alive today. So, the dinosaurs didn't lose. They changed, they adapted, they became something new. And they're still here. And maybe that's the final lesson of the Triassic. That success isn't measured in dominance. It's measured in persistence, in adaptability, in the ability to change when the world changes, to become something new rather than clinging to what you were. The Crurotarsans couldn't do that. They were too specialized, too finely tuned to the Triassic world. When that world ended, they ended with it, except for the aquatic lineages, which were flexible enough to survive in a different niche. The dinosaurs could do that. They were generalists at the right moment, and when opportunity arose, they seized it. They diversified, they specialized. And eventually, when their world ended, the birds survived because they were flexible enough to adapt again. Mammals did the same thing. We were marginal for 165 million years, small, nocturnal, insignificant. But we survived, and when the non-avian dinosaurs died, we inherited their niches, and we diversified. And here we are, and maybe someday something will inherit our niches. When we're gone, when our civilization has collapsed and our species is extinct, something will survive, and it will evolve, and it will become something new. And it will look back at our fossils the way we look at Postosuchus and Herrerasaurus, with curiosity, with wonder, trying to understand what we were and why we disappeared. And the answer will be the same. We were dominant for a time. We were successful, but the world changed, and we couldn't adapt. Or we caused the change and couldn't stop it, and we died. And something else survived. That's the pattern. That's the cycle. That's how life works. And the Triassic, more than any other period, shows us this. Because the Triassic was a time of transitions, of turnovers, of the old dying and the new being born. It was a bridge between worlds, a hinge point, a moment when everything that came before ended and everything that came after began. It was the birth of the dinosaurs. But it was also the death of the Crurotarsans. And both are equally important, because you can't have one without the other. Death creates the space for life. Extinction creates the opportunity for evolution. That's the alchemy of deep time. The transmutation of catastrophe into creativity, of endings into beginnings. of death into rebirth. The Triassic was hell, a world recovering from the worst extinction in history, a world torn by volcanism and climate change and ecological collapse, a world where survival was uncertain and dominance was fleeting. But it was also the crucible, the forge, the place where the Mesozoic was born, where the dinosaurs, those marginal failures, became the rulers of the planet, where birds, the most successful vertebrates alive today, trace their lineage. Without the Triassic, the world we know wouldn't exist. The ecosystems we study, the species we marvel at, the evolutionary pathways that produced us, all of it required the Triassic, required the extinctions, the suffering, the death. Because that's how evolution works. Through trial and error, through catastrophe and survival, through death and rebirth. It's not fair, it's not kind, it's not gentle, but it's effective. It produces diversity, complexity, beauty, innovation. It produces dinosaurs and birds and mammals and humans. It produces all the wonders of the natural world, at the cost of countless extinctions, countless species dying, countless lineages ending. But life, the process itself, continues, unbroken, unstoppable. The chain stretching back 3.5 billion years and forward into a future we can't imagine. The Triassic is one link in that chain, an important one, a pivotal one, but just one. There were chains before it, and there will be chains after it. The story of life is longer than any period, longer than any era, longer than any eon, and we're part of it. We're one link in the chain, not the final link, not the most important link, just a link, like the dinosaurs, like the Crurotarsans, like every species that's ever lived. And someday our link will end, our chapter will close, our fossils will be buried and forgotten, or studied by whatever comes after us, and the chain will continue. Because that's what it does, it continues. The Triassic teaches us to accept this, to embrace it even. Because there's beauty in impermanence. There's meaning in being part of something larger than ourselves, something ancient and ongoing and infinitely creative. We are the universe experiencing itself. Atoms arranged in such a way that they can contemplate atoms. We are stardust that became life, that became consciousness that looks back at the stars and understands where it came from. That's a miracle. But it's a temporary one. A brief flowering of complexity in an ocean of entropy. A candle that burns brightly for a moment, then goes out. But while it burns, it illuminates, it creates, it means something. And that's enough. It has to be. Because permanence isn't an option. Not for us. Not for anyone. The Triassic proves it. The dinosaurs prove it. The Crurotarsans prove it. Every extinction proves it. But the Triassic also proves something else. That endings are not the end. That from the ashes of the old, the new arises. That catastrophe is not closure, but transition. That death is not the opposite of life, but part of it. The Crurotarsans died so the dinosaurs could live. The dinosaurs died so the mammals could live. And someday, we'll die so something else can live. And that something will be beautiful and strange and unexpected, and it will look back at us and wonder. Just as we look back at Paustosuchus and Herrerasaurus and wonder. What were they? Why did they fail? What would the world have been like if they'd succeeded? We'll never know. But we can imagine. And in imagining, we connect to deep time, to the vast sweep of evolution, to the countless species that came before us, and the countless more that will come after. The Triassic was their world. The Cenozoic is ours. The future belongs to someone else, and that's how it should be. That's how it always has been. That's how it always will be. Life is a relay race. Each species runs its leg, then passes the baton. Some run longer than others, some run faster, but everyone eventually finishes, and someone else takes the baton and keeps running. The dinosaurs ran for 165 million years, an extraordinary run. But it ended, and mammals took the baton, and we've been running for 66 million years. Not as long, not yet, but respectable. And someday we'll pass the baton too, to someone else, someone we can't imagine, someone who will run their own race, in their own time, in their own way, and the race will continue. Because that's what life does. It continues, through catastrophe and calm, through extinction and radiation, through death and rebirth. The Triassic is proof. The dinosaurs are proof. We are proof. Life finds a way, always has, always will. And that's the final lesson, the ultimate takeaway from the Triassic, from the dinosaurs, from 3.5 billion years of evolution. Life persists, life adapts, life continues, no matter what.